Okay, today we're gonna see timing circuits, part 2. Um, we will delay a pulse with two edge detectors. This is the negative edge detector in series with a second one. So they are in cascade and we will delay a pulse. This will be for an oscillator, but first let's see how the pulse is delayed. So you apply a pulse here from high to low logic at the rising edge. Let's see what happens. So when you apply here 5 volts first on this pulse, you have 5 volts here and 5 volts. So there's no bias and no voltage, and the capacitor will be open, and because it is open, R1 pulls up the input to a logic high. So this will be a logic 1 and this will be a logic 0. Because this is in logic 0, the capacitor is already charged thanks to this current. So because it is charged, it's logic 1, and right here you have logic 0. This is the initial state. Now when you trigger the input at the falling edge, now you have a 0 volts right here, equivalent to 0 volts, and the capacitor gets closed in time t equal to 0. It is a closed circuit. So you have here the voltage across the capacitor behaving like this. It goes to 0 volts and then it starts charging, okay, to VDD. So because right here you have a transient 0 thanks to the voltage across the capacitor 1, which is equal to the applied voltage VDD times 1 minus e to the negative t over RC. Okay, that's the voltage across this capacitor. Because it is 0, right here after this 0 you have a logic 1. Once the capacitor reaches the threshold, positive threshold, the input went to 0 and now it goes back to logic 1. So this one goes to logic 0. Okay, and this period we're gonna call it T1. T1 can be solved by solving, can be obtained by solving this equation. Okay, now at the rising edge of this signal you get another pulse here, and this pulse triggers this Schmitt trigger, and then you have another positive pulse, and the voltage across capacitor 2 is equal to this formula, voltage times 1 minus e R2 over C2. We can call this T2, and right here is R1 C1. So if you need to know the period of this pulse from here to here, you solve it from here. So to solving for T1 in this formula, T1 of course you can multiply B times this and then pass it to the other side. T1 you can do that. T1 will be equal to R1 C1 ln of the voltage applied over the voltage applied minus the final voltage of the capacitor. In this case will be the threshold, the positive threshold, so VT plus. For T2, from here it will be equal to R2 C2 ln of VDD over VDD minus VT plus. The only thing that changes is the capacitor. So the frequency, well, there's no frequency at this moment. We only have the two pulses, the period of T1, which we can define as this period from here to here, T1, and this is T2. Okay. So you apply a pulse, you obtain T1, and when T1 falls, T1 starts, and they are they are in sequence. When this pulse ends, the other one starts. So to make an oscillator from this circuit, I just need to make a feedback, and I'm just going to remove these levers. The power continues right there. Of course, this is VDD, this is VDD. So if I remove this and I make a feedback loop, this becomes an oscillator, because when this pulse ends, it'll trigger the first edge detector. So two edge detectors with a feedback loop can make a stable or a multi-vibrator, an oscillator we can call it. And so it works the same way. It triggers in sequence, and the feedback triggers again the circuit. So the frequency is 1 over T1 plus T2, and you know both periods, so the frequency is 1 over, and notice that you can do factorization because the resistors are different. So R1, C1, ln of all this. Let's say this is constant, a constant one that you get, plus R2, C2, ln of K2. K2 is this constant. Then you can reduce it by using other logarithmic properties, but this is a frequency. So how the circuit works as an oscillator, that's defined in this circuit, in this timing diagram. When inverter 2, this one, goes down, it triggers the first one. So this is the voltage across capacitor 1, BC1, and then the capacitor charges until it reaches the trigger positive threshold. And then when this pulse ends on the inverter 1, when this pulse ends, triggers this capacitor, or it represents this voltage in this capacitor, and then starts charging. So you see, every time this one is finished, it triggers the first one. So they are back and forth triggering by themselves, and that's an oscillator. Now the homework for you, which will be due by the end of the month, your homework will be this. I will be putting the resistors to ground. So I'm going to remove this. You have these equations, and these equations will be different. Let me erase this. So your homework would be, if I ground this resistor 1 and resistor 2, okay? Now this is a circuit that it is triggered at the rising edge, not the falling edge. So you will have this type of signal here, and this type of signal of voltage here. So it is the voltage across resistor 1 and resistor 2. So you have to get, using this formula, the current 1. Now current 1 will go this way with respect to time, and right here you will have current 2 with respect to time. From those formulas, from those equations, you will get, remember, we can define I1 of t is equal to b over R1 times C to the negative T1 over R1 C1. So this is the maximum current in the time equal to 0. So this is why some authors define it as I0, the initial current, which is the maximum. Okay, and current 2 of T will be equal to V over R2. This voltage is the maximum voltage you get here at the rising edge. And that's e to the negative T2 over R2 C2. So solve for, once you have both formulas, solve for T1, solve for T2, and find the frequency formula, okay, when they are in feedback. So this is your homework. As I said, it is due by the end of the month. So see, this is my today's lesson on how to use two edge detectors to create an oscillator. In this case, these are edge detectors that detect the rising edge of the signal. So positive edge detectors. Okay, that's your homework, and that's all for today.